Hey everybody, Mr. Klein here. I am going to talk about example number 2. Felt like you could probably use one more example. So here we go. It starts raining at noon and it rains really hard for 4.5 hours. Suppose the rate at which rain falls in inches per hour, t hours after noon, is given by this function. You are concerned that about your basement flooding. Generally, a basement like yours is safe as long as you don't get more than 4 inches of rain over the course of those 4.5 hours. So the question in this problem is going to be about, do you get more or less than 4 inches of rain, which is a lot of rain outside. Okay. And in order to answer that question, let's think about this. The units here are in inches per hour. So if we want to know the number of inches, we have to multiply by hours. So we're given a rate. We want a total. Anytime you're given a rate and you want a total, it means it's time for us to do a definite integral. So what we're interested in calculating for this problem is this: the integral from time 0 to time 4.5 of the function 2e to the negative 0.5t. I could have written r of t just as easily there, dt. We want to know what that is equal to. So this is a multi-step problem. The first step is to draw a graph of what you are working with here. So I'm going to put r of t on this axis, and I'm going to put t on this axis, and I want to know what it looks like from about 0 to 4.5. So we grab our calculator, and in our calculator, I want you to put the r of t into y1. Once you've got that, you're going to go to the window. You're going to change the window from 0 to 4.5. You are then going to hit zoom and select zoom fit. I know I say this over and over again, but zoom fit is going to work out what the y values are for you. So I'm going to go ahead and hit enter. So I can see that the rate is going down, 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 down over time here. There's my graph. I do like to go back here and change the minimum to 0. Go one more time. There's what our graph looks like. So I'm looking at something like this. Cool. All right. So with that in mind, think of that as like step number 1 is to get yourself a graph. Step number 2 is to figure out what your change in time. This is the same as the change in x is going to be. Recall that you do that by taking the b value, we call this, and subtracting from it the a value, is what we call the start point, and then divide by the number of subdivisions. So this says find the trapezoid rule approximation with 3 subintervals. So I'm going to divide by 3. That's going to give us 1.5. Okay. So that's step number 2. Now that you know that our intervals are going to have a width of 1.5, you can come over here and you can mark those intervals. So the first one will be 1.5. Add 1.5 onto that. The second one will be at 3. Add 1.5 onto that. The last one will be at 4.5. So there's our intervals, and our trapezoid is going to look something like this. Boom, boom, boom. As part of step 3, you're going to need to figure out what the bases are. And there's 1, 2, 3, 4 of those bases. And here's where your calculator comes in once again. There's a couple different ways that you can get it. One option would be to do second calc and then value. And then I could put in, I want 0. And it will tell me that this base has a value of 2. And then I could go second calc, value, and then put in 1.5. And it would tell me that the next one is 0.945. Let's go to 3 decimal places on these. The other way that you can get those values would be to go to the table Now I have mine set to ask right here. Second table set, ask. And once I've got that, I can pretty quickly go in 0, 1.5, 3, and 4.5. This is my preferred method. You'll see the numbers I get are, let's see, 0.446 and 0.211. Okay, so that's step number 3 to get those 4 values. Step number 4 is to actually write out our trapezoid calculations. So T3 would be equal to, and yes, I do want to see these. Half of something times a sum plus half of something times a sum plus half of something times a sum. All of our heights here, here, and here are going to be the same. They're all 1.5. For the first trapezoid, our bases are 2 and 0.945. For the second one, our bases are 0.945, right here, and 0.446. Nope, I should have put the 1.5 here. For the last one, you can see here's the first base, here's the second base. So those would be 0.446 and 0.211. So you grab your calculator and you punch this out. Now you guys know that I am calculator lazy. So one thing that I'm going to do is I'm going to take the half and the 1.5 and I'm going to factor those out. And then I'm just going to deal with this separately. And what I see over here is that I've got a 2, and then I've got 2 of these 0.945s. And then I've got 2 of these 0.446s, and then I've got 1.211, end parenthesis. If you have no idea what I'm talking about, what I was just saying is I got 1 of these, 2 of these, 2 of these, and 1 of these. I hit enter, and I get an answer. And that answer is, I guess I'll write it down here, 3.74, we'll call it. This is a real world problem. It has units. What are the units? Well, we calculated them already. It was inches per hour multiplied by hours is inches. So this is our number of inches of rain. Do you have to have those units included? Yeah, you do. Okay, so there is our number. Answer to A. B says, explain whether there is sufficient information to conclude that your basement will or will not flood. All right, so our prediction was 3.74, and we know we have to have less than 4. Now, is this an over or an under approximation? Let's look over here. The curve is concave up, and because the curve is concave up, you can see that the trapezoids are above it. So our answer is going to be yes. If you ask for a reason why, you're going to say, well, 3.74 is less than 4, and it is an over approximation. So we know the inches of rain must be smaller than 4. And we're happy.